Hi, Professor.
Hey, how's it going? Sure. Yeah. Oh, let's do March 2nd. Yeah, I forgot to change it on campus. Yeah. Move it up?
Yeah,
I don't know if that's gonna be a popular decision.
it's okay. I want them to learn. Xavier agrees. No.
No, it'll be the 2nd. That's Sunday, I think, right? 2nd?
Yeah.
Okay. Yeah, that's probably why I did that, because Friday, so I'm not grading over the weekend, so yeah, I'll put it Sunday.
So you want to be, want to be the 26th? Yeah, I'm not making this up, he's telling me.
A couple people were talking about last week. Sometime. Just take the summer class.
So if you're taking the labs this summer, 476 A and B,
Mhm.
we know who needs to take it this summer. So when you sign up for it, you'll be on the wait list, but then we'll automatically give you a permit before summer starts.
Okay.
Yeah, the reason we do that is just to make sure everyone who needs it is in it.
It's
So
neat, okay.
and also because it's once the student's in the class, it's really hard to kick them out. So sometimes like we have juniors sign up for the course and they don't really take it. We do this just to make sure that there's enough for all the seniors taking it.
Okay. I just heard it on my code. I mean,
Oh, no, yeah, you'll be fine. Mhm. What's up?
Question.
Yep. Mhm.
So for problem 2, we use just to sign the
Yep.
Would know how I start this.
Yeah, so you have a triangular cross section, right?
Mhm.
And you're given constraints in terms of how big one four dimensions.
Yeah.
And so basically you want to maximize this. In one way, so the thing you're really kind of playing with right now is the geometry. So if you look at the geometrical features here, you look at the ratio of the perimeter to the cross section area. So how can you maximize that ratio? That's the cross section area based on the.
He was not here this morning.
The limitation we're given.
He wasn't
apply to
in,
the-
Just whatever is not dimension, it has, that's the limitation.
Oh, God.
So the Z direction is probably gonna be the most limited, that's one long.
Thank you.
You.
I'm prepared. Is your pen for
Yo, it's next.
Yeah. Is your pen charged? You're prepared. You can have it. Hi, Dr. Chen.
Hey, how's it going? Good?
I'm enjoying the warm.
Oh, I love it, it's great.
Whatever. Like, all right. But he's doing the code, I'm doing.
There's like no way to figure it out on your own.
Like discussion. How to do it. I would just guess.
Oh, it's easy.
It's really weird.
But I think I actually like to do the theory. You just copy and paste it.
Yeah, he did the same. He just copied. But it's not a big theory.
Yeah. Yeah, no, very
So
good.
I like.
You just have to do like everything. That's like basically.
Just wait on that.
Even that wasn't like either no or like.
It's just like everything is not. Yeah, it's always complete. That would be. But since you don't have a lot of things,
All right, it's 1 o'clock, let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. You guys probably have midterms and stuff this week, so I know part of the semester when things get really busy. Speaking of midterm exams, we do have one for this class coming up. So our midterm exam is going to be not this Thursday, but next Thursday. So that's going to be March 6th. So some information on the exam. So in terms of the content that's going to be on the exam, it's going to be the first three homeworks. So homeworks 1, 2, and 3 are probably, you know, that's probably your first stop in terms of studying. You know, the problems are going to be very similar to what's on the homeworks because I write both, and so you know, if you can do the homeworks really well, then I always say that you're in good shape. The other thing I posted on Canvas, you may have noticed this for the weekly page for week 6, is that I posted a study guide as well. So the study guide is kind of a good place to go to kind of just get kind of like a bird's eye view of everything that we've covered up to this point. And it'll help you kind of more with the conceptual questions on the exam itself. Okay. So definitely check those out. And of course, you know, you're going to want to study your own notes, the lecture notes, textbook if you have it as well. So, you know, all of that is kind of good stuff. But homeworks 1, 2, and 3 and the study guide, I would recommend that for everyone to use that to prepare for the exam. Okay. Question, yes.
The cheat sheet, anything you want or only?
Anything you want. Yeah. Anything except for the answers to the exam, which would be very hard because I haven't written the exam yet. So unless you know the future, then you can put anything that you want on the cheat sheet. Yep. Speaking of cheat sheet, you can also write it, you can type it, whatever is most comfortable to you. I've seen there's a strategy of people just taking my lecture notes and just making it really, really tiny and then putting it all on the cheat sheet. That's certainly a strategy. It's not a recommended strategy. Because you have to be able to read the cheat sheet while you're on the exam. So, but you know, with the cheat sheet, I always tell people, you know, sometimes less is more with the cheat sheet. I think people try to just put everything they can on the cheat sheet and, you know, and not really kind of look over, not really study in the hopes that, you know, you can just refer to it on the exam. You know, the exam's only 75 minutes. And I think what I've been seeing a lot kind of in recent years is that, you know, people, I think they put a lot on their study guide, but then, or they put a lot on their cheat sheet. But then people spend just a lot of time on the exam, just like checking through the cheat sheet and not enough time actually doing the exam itself. And so usually what I recommend for the cheat sheet is, you know, actually spend a good amount of time actually condensing a lot of the information. Part of studying is, you know, taking all this, you know, we've done a lot so far in this class and then condensing that onto like a small cheat sheet. And then, you know, once you do that, just the process of kind of condensing that information helps you process it, helps you kind of understand it a bit better. And then, you know, you'll spend less time during the exam reading the cheat sheet because you've already kind of committed it to your memory. So, you know, for the cheat sheet, you can do whatever you want with it, but you know, that's kind of my recommendation for how to approach that. Okay. Question, yes. You can keep it after. Yeah, because this class is gonna have a final exam too. So some people like to use the cheat sheet from the midterm on the final. So, yeah. In terms of the format for the exam, you can expect there to be 4 short answer conceptual questions. So those are very similar to what you've been seeing on the homework. So those will be kind of, you know, you answer, you know, I'll ask you something conceptual about the course so far, and then you'll answer in maybe 2 to 3 sentences. Maybe I'll have you draw a diagram or something like that. So that's worth 40% of the points. And then the other 60% of the points are going to be problem solving type questions. So those would be, you know, like your thermal circuit type problems, your heat equation type problems, your lump capacitance type problems. And so, you know, like kind of all the examples I've been doing in class, all the problems you've been doing on the homework. So that'll be worth 60% of the points. Okay. In terms of what else you can bring, writing utensil, of course, pencil, pen, whatever you're most comfortable with. Bring a calculator too. So you're gonna need a calculator to do the calculations. Scientific calculator, graphing calculator, doesn't matter to me. As long as it's not your phone, then you know you can use any calculator that you want. And you know, I know some people get thirsty during the exam too, so bring your water bottle and stuff like that. All right, any questions on the exam? Exam's going to be in person, and so it's, you know, there are 3 days that I require you to come in person in the class. So that's midterm 1, midterm 2, and the final exam. So there's no plans to offer the exam online. So, you know, for those of you who typically attend on Zoom, you know, just kind of plan ahead. Just make sure you have enough time to find parking and make it to the classroom on time. Okay. All right. And so that's, you know, that's the exam. And just remember, I have office hours today. I have office hours on Thursday, and I have office hours next week as well. So Monday, Tuesday. Well, and then the class will happen before the Thursday office hours, but, you know, try to make use of that. Send me questions over email, and, you know, I'm always happy to help you out. Okay. All right. And so, oh, another announcement. So I realized that I forgot to change the due date on homework 3. Someone pointed out before the class. I think on the PDF of the homework 3, it says that it's due this Sunday, March 2nd. But I think on Canvas, I left the due date as the 28th. And so I need to change that on Canvas. So the due date is going to be on this Sunday, March 2nd. Yeah. Oh, and by the way, so the solutions for homework 1 and 2, they should be up on Canvas already. Solutions for homework 3, since, you know, I know you guys would like to have that to study for the exam. I probably post those on either Monday or Tuesday of next week for you guys to look at. Okay. Okay. All right. And so with that, the plan for today is we're just going to continue with what we left off with last time. So I think we kind of started an example last time. So I kind of want to pick up with that again. And then we're going to finish up the lump capacitance method today. So my goal for today is to finish up unsteady conduction. So after today, you shouldn't, you know, everything that we cover on Thursday and Tuesday is not going to be on the midterm. Today should hopefully be the last day. But if there's just a little bit we have to cover on Thursday to finish up, we might have to do that. But I'm hoping to finish up everything today. Okay. All right. Any questions on anything, exam, you know, content, homeworks, anything before we get started? Okay. All right. So I'm just going to scroll up here. So, you know, hopefully you guys wrote this down last time because, you know, it is a little bit lengthy. And so we were working on an example, kind of another unsteady conduction example. Okay. And so in this example here, we are designing a spherical thermocouple to measure the temperature of a hot gas that's blowing by. Okay. So, you know, we kind of introduced this example as a way to kind of hammer home this idea of the Biot number and the validity of the lump capacitance method. Okay. So our spherical thermocouple has parameters that we have listed here. So it's made of a material with a thermal conductivity of 20 watts per meter degree C. It has a heat capacity of 400 joules per kilogram degree C. Its density is 8,500 kilograms per meter cubed. And it's starting with a temperature of 25 degrees C. So it's starting at room temperature. Okay. The environment that we're putting it in, it's going to be some kind of hot gas from some kind of experiment that's going to be blowing by it. So the temperature of that gas is going to be 200 degrees C. So it's very, very hot. It has a convection coefficient of 400 watts per meter squared degree C. Okay. So if you notice, you know, one thing I did not give you in this problem is the radius of the spherical thermocouple. Okay. Okay, and so that's actually what we're going to solve for in part 1 of this problem, because, you know, if you remember what we discussed last time is that not every unsteady situation we can analyze with the lump capacitance method, because really it all depends on whether we can make our lump capacitance assumption. And so the first part of this problem is we are going to design this thermocouple so that the lump capacitance method is actually valid. Okay, so we're going to factor in the Biot number for that. And in part 2, we're actually going to solve for the time evolution of temperature. So we're going to solve the lump capacitance equation and find out how long it's going to take the thermocouple to reach a temperature of 199 degrees C, which is essentially the same temperature as the gas around it. Okay. Okay. All right. So in case you're still kind of writing down from last, I'll leave this up for just maybe a second or two.
Surface temperature of the thermocouple?
So T naught is the temperature of the entire thermocouple. Yeah, exactly. Yeah. So remember our key assumption with lump capacitance is that whatever object we're considering is the same uniform temperature all throughout. Because if you have any spatial variations of temperature, the lump capacitance method would not apply in those cases. Okay. All right. So let's go ahead and solve this. Okay. Okay. So part 1. So part 1 is we need to design the thermocouple so that the lump capacitance method is valid. Okay. All right, so let me go ahead and draw the thermocouple here again. Okay. And like I mentioned before, the only parameter that we're not given in this thermocouple is the radius of the sphere. Okay. So essentially what this part of the problem is asking us to do is to design that radius or select a radius so that we can actually apply the lump capacitance method, okay? And like I mentioned before, the fact, or the criteria that we have here for determining whether the lump capacitance is valid is basically making sure that our entire thermocouple is of a uniform temperature. So there's no difference in temperature between the surface and the core of this thermocouple. Okay. So if we measure the temperature at the surface, TS, and the temperature at the core, we'll call it T, I used T naught already, we'll call it TC, right? If our lump capacitance method is supposed to be valid, then TS and T core, these are going to be the same at all times, okay? Even when the temperature around it is changing, even when we're exposing it to the hot gas, what we're saying here is that the thermocouple has to be small enough so that there's no difference in temperature between the surface and the core, okay? Right, so the main design consideration here is that the thermocouple has to be small enough, a radius has to be small enough in order for this to occur. Okay. And generally, that's kind of what you see in when applying the lump capacitance method to a lot of different situations, that, lump capacitance really only is valid for relatively small objects, because, if you have a small object, it doesn't take that long for heat to propagate all the way through. And so, it's only valid for those cases. Of course, it's not just limited to small objects, but generally that's kind of what you see the most, okay? So essentially, in order for our lump capacitance method to be valid, it's going to place an upper limit in terms of what our radius can be, okay? Okay, so conceptually, that's what it means for the lump capacitance method to be valid. Mathematically, the way that we do this, or the way that we compute it, is by computing the Biot number. Okay. So remember, the Biot number has the formula from last time that we said was H times LC divided by K. Okay. And in order for the lump capacitance method to be valid, the Biot number has to be less than 0.1. Okay. All right. It would be better if the Biot number was smaller than that, but the highest the Biot number can be is 0.1 in order for our lump capacitance method to be valid. Okay. All right, and so if we look at the parameters for this problem, we are given H, right? So H is the convection coefficient of the hot gas. We know that already. This is 400 watts per meter squared degree C. And we know the thermal conductivity of the thermocouple. This is 20 watts per meter degree C, okay? And so the only thing that we have to determine here, or the only thing that we can solve for, is this characteristic length. Okay. Which eventually is going to equate to the radius of our sphere. Okay. And it's not exactly the radius, but it'll be some expression that includes the radius. Okay, because if you remember from last time, the way that we compute this characteristic length, because generally you're going to be applying this methodology for a lot of kind of complex geometries. The most reliable way to compute this is it's going to be the volume of the object that you're considering divided by its surface area. Okay. Okay. And so we know that our thermocouple here is a sphere. And so let's go ahead and plug in the formulas for the volume and surface area. So volume of a sphere is going to be 4/3 pi times the radius cubed. Okay. And then the surface area for a sphere is 4 times pi times the radius squared. Okay. Okay, so let's go ahead and solve for this. And so we're going to see we have the 4s are going to cancel out. The factors of pi are going to cancel out. 2 of the radii are going to cancel out. Okay. And so for a sphere, our characteristic length here is r divided by 3. Okay. Bless you. Okay, so let's go ahead and plug this expression into our Biot criteria here. And let's go ahead and plug in the values for h and k as well, right? And so our Biot criteria says that when we plug in h, it's 400 times r divided by 3 times 20. Okay. So, you know, the Biot criteria, it's an inequality criteria, but if you want to find the maximum radius that we can have, we can set it equal to 0.1. Okay. But basically anything smaller than the radius that we solve for is going to be good. Okay. Okay. So if we go ahead and solve for r here, so we just rearrange some of the terms. We have r is equal to 0.1 times 60 divided by 400. Okay. And then if we punch that into a calculator really quick, because for some reason I have the numbers wrong on my notes here, that is 0.015 meters, which if you want to put it in centimeters is 1.5 centimeters. All right, so what this is telling us is that the radius of our thermocouple can be at most 1.5 centimeters in order for the lump capacitance method to be valid. It could be less than this, and so you can have a thermocouple with the radius of 1 centimeter and still be fine. But you know, the biggest it can be is 1.5 in order for us to use our lump capacitance. Okay. All right, any questions on this example here? Okay, good. Okay, and so now that we know the radius, now our thermocouple is fully designed or fully specified here. And so in part 2 of this problem, we want to find out how long is it going to take until the thermocouple reaches 199 degrees Celsius. Okay. So for this problem here, we're going to need our full lump capacitance solution here. Okay. So we already solved for the solution to the lump capacitance equation, right? And so for a general situation like this with only, you know, the only heat transfer we have is convection, then our solution, so remember we obtained this after solving the lump capacitance equation. Okay. So I'm going to skip that step, but you know, we did that, you know, last time. Okay. So remember, we had that first order differential equation, and we solved it with integrating factor, and we got this question. Yes. It'll say on the exam. And so if on the exam I want you to derive it from the differential equation, I'll say that. If it doesn't say that, you can just skip right to the solution. Yeah. Okay, so our solution looked like this. E raised to the minus HAS over rho VC times T. Okay. All right, everything in this exponent we know. Okay. So we're given the convection coefficient. We can compute the surface area because now we know the radius. The density we were given to us in the problem. The volume, again, we can compute that if we, based on the radius that we computed in the last step. And the heat capacity was given to us in the problem. Okay. This one we can also compute as well. We may have to compute this a bit first, because remember, this is the initial excess temperature. Okay. And remember, our formula for the initial excess temperature is the difference in temperature between the object and the surrounding fluid. Okay. So this is T naught minus T infinity. Okay. We know from this problem that the initial temperature of this object was 25 degrees C. And then the initial fluid temperature here is 200 degrees C. Okay. And so we take the difference. This is minus 175 degrees C. Okay. All right. So if you plug all that in, well, it's just numbers from there. So you have theta of T is equal to theta naught E raised to the minus HAS over rho VC times T. Okay. All right. So basically we have everything for our full solution here. A couple of things you may have to compute, like the volume, the surface area, but we have it all. Okay. So what this problem is asking us to do is it's asking us how long is it going to take for the thermocouple to reach a temperature of 199 degrees C. Okay. So in this problem, we're solving for time. Okay. And we're solving for a specific time when theta reaches a particular value. Right. Okay. So first, let's find out what the value of theta is going to be when the thermocouple reaches 199 degrees C. Okay. Okay. Because remember, when we're solving our lump capacitance equation, we're solving in terms of theta, not in terms of T. Okay. But when T is 199, we can compute its theta very easily. Okay. So remember, theta is just whatever temperature the thermocouple is at minus the fluid temperature. Okay. Oops. Just 200, excuse me. Okay. And so when the temperature of the thermocouple was 199, let's just go ahead and plug that in there. And so we have theta is equal to 199 minus 200. Okay. And so that, of course, is equal to -1. Okay. And so what we're going to do is we're going to plug -1 into that expression up there. Okay. So we're going to -1 is equal to minus 175 E raised to the minus HAS over rho VC times T. Okay. And then from this expression here, we can solve for T. Okay. Okay, and so of course to solve for T, we can divide both sides by 175. And so we have 1 divided by 175 is equal to E raised to the minus HAS divided by rho VC times T. Okay. Okay. And so from here, to solve for T, we need to cancel out the exponent there. So let's take the natural logarithm of both sides. Okay. So we're going to take the natural log. The natural log is going to cancel out with the E. And so all we're left with here is natural log of 1 divided by 175 is equal to minus HAS over rho VC times T. Okay. And so from here, it's just algebra. You're just going to punch things into a calculator. Okay. And so if we do that, we get T is equal to 5.2 seconds. Bless you. Okay. So that's kind of how you solve these problems when you're solving for T. So when you're solving for time in these lump capacitance solutions, you're usually going to plug in something for the excess temperature, and then you're going to have one algebraic expression to solve for T, kind of like what we did in here. Okay. All right. Any questions on how we did this? How we did this example here? Okay. All right. So that's the I would say kind of the simple form for lump capacitance, where we only consider just convection. But really, for a more general situation, you can have different sources of heating as well. And so you can have an object that maybe is producing heat. You may have an object that's being, that's getting heat from another source, or like from a heat flux, or it might be getting radiation as well. So we can actually modify our lump capacitance equation to account for these kind of more general situations. Okay. So this is kind of the last topic that we'll cover in this section here. Okay. So this is called general lump capacitance analysis. Okay. Okay. So far, the only source of heating that we've, or the only source of heat that we've been kind of considering for our unsteady situations have been convection. Okay. And so that gave rise to the kind of the lump capacitance ordinary differential equation that we looked at before. Okay. But in reality, there are lots of different sources of heating and heat loss that we can consider as well. Okay. So some examples of this would be maybe a prescribed heat flux. Okay. Maybe thermal generation. Okay. And 3, radiation. Okay. Now, radiation we haven't talked about really at all in this class yet, but for radiation, we're just going to assume that it's just another form of heat flux. Okay, so radiation is going to apply heat to an object, and that's either going to heat it up or it could cool it down as well. So maybe our object is so hot that it's radiating heat outwards as well, okay? But, you know, kind of the upside to this is that we have to consider, you know, all of these sources if we're going to do kind of a more general, unsteady lump capacitance analysis, okay? Okay. And so if I were to kind of illustrate this, right? Let me just draw a square object for now, okay? And if we do an energy balance on this object, right? So kind of just like we did last week when we considered just the kind of the initial form for lump capacitance, the only kind of heat that we had lost here was heat lost due to convection. Okay. All right. And also what we had was that, you know, to kind of make this balance is that we needed an expression for the internal energy of the object. Okay. The internal energy represents the temperature of the object itself. Okay. So our energy balance before was simply just that the energy or the change in internal energy of the object was equal to either the heat lost or the heat gained due to convection. Okay. And this kind of formed the basis of our lump capacitance equation, right? Yeah, question.
You just those two terms.
Yeah, so we're going to add more terms to this, but this is kind of just where we started with last time. But here we're going to add more terms. Yeah. Let me actually draw the convection going by. So. Okay, so far we've only considered convection, but what if we also included, you know, let's say that this object is being heated by, you know, some kind of heater on the outside, right? So in other words, you know, maybe there's some kind of heat flux that's being applied onto one side of the object, okay? So we'll call this Q S double prime, okay? So this QS double prime here, this is some kind of applied heat flux. Okay. And so that heat flux can come from a number of different sources. Maybe it's a heater that's applying this, or maybe there's some kind of fire or flame that's applying this heat flux, right? And so we can modify our equation here. And so not only do we have Q convection, but we're also going to have QS double prime, okay? But remember, QS double prime is a heat flux. And so in order to make sure that the units match up, we have to multiply QS here by some kind of surface area. We'll call it AS, okay? All right, so that's another source that can add to our lump capacitance situation. Okay? And by the way, you're not just limited to just one heat flux either. And so a lot of times you're gonna have multiple heat fluxes as well. So maybe you have another heat flux that's coming from the bottom, right? So we'll call this Q2 double prime. And so you can add that to your equation as well. But, you know, I'm just going to sum up everything for one, but just know that, you know, for any given problem, you can have multiple sources of heat flux. Okay? All right, so I'm not going to add this Q2 to the equation down there just because I want to keep it clean, but just know that, you know, there's more than one heat flux that you can apply. Okay. Okay. All right, another source that we can consider is maybe the object itself is producing heat. Okay. So maybe we have an object that's either producing heat or maybe it's absorbing heat, okay? So remember, we used our symbol Q dot here to denote thermal generation. Okay. And so we can add that term to our energy balance here. So it's going to be Q dot. And the units for Q dot is always watts per volume. And so we need to multiply this by the volume of the object, okay? All right. And I think this is appropriate because remember, generally, you know, for the most part, we don't include radiation just because a lot of times the contribution from radiation is really small. But let's say if you have an application that's in space, so you're designing like a satellite or a cube satellite or something like that, then radiation in that case is going to be significant. And so you can also have radiation that's being applied to your object as well. Okay. I don't get to bust out the cosmic ink every now and then, so I'll take this opportunity. Okay. And so you might have a contribution from the radiation as well. Although, for the most part, we are going to ignore that for most of our cases, but technically it is possible. Okay. Okay. And so if we look at this, right? Now our energy balance with all these additional sources or additional kind of contributions to lump capacitance, now our energy balance is a lot more complicated. Question, yes.
Right now, you edit the terms, is there any place where you're gonna subtract them?
Yeah, so right now I drew all these terms assuming that heat is entering the object, but you can also have situations where the heat is leaving the object from these as well. Actually, convection, if I want to be consistent, technically the convection I drew here going out. And so convection should actually be negative here because I drew the Q convection going outwards that way. But for any of these terms, they could also be negative if heat is leaving the object.
You said any of the terms.
Yes. Mm-hmm. Yeah. So for thermal generation, you could have an object that, maybe is, maybe there's some kind of endothermic reaction taking place. And so maybe there's something that's absorbing heat to power some kind of, chemical or electrical process. And so that would be a situation where Q dot would be negative. But that's kind of rare also too. But yeah, technically any of these terms can be negative depending on the sign of the object. Okay. Okay. All right, and so what we can do from here, just like we did before, is we can take this energy balance and we can kind of represent each term kind of with or put kind of each term in terms of the kind of the temperature of the object. Okay. Because essentially what we want to get is we want to be able to get an ordinary differential equation to solve for the temperature of the object itself. Okay. So, we did this kind of in the simple form for lump capacitance. So we plugged in basically Newton's law of cooling for the convection term. We plugged in kind of the expression for the change in internal energy in terms of the time derivative of temperature. Okay. Actually, technically, those are the only two places where we can actually apply those. And so, we're going to plug in for E internal and Q convection, just like before. But actually, the new terms that we've added are kind of mostly, they mostly are kind of stay as they are. Okay. Okay. And so if we do that, we end up with the following expression here. So we have the change in internal energy is rho, the density, multiplied by V, the volume, times the heat capacity, times dt. Okay. So that's what we get when we plug in the change in internal energy. Okay. This is equal to minus H times the surface area times Newton's law of cooling. So we have T of the object minus T infinity. Okay. So that is Q convection. So that's Newton's law of cooling. Okay. For the prescribed heat flux, there's really not much we can do with that because usually when you have a heat flux, it's usually known how much heat you're applying to the object. And so we're just going to leave this alone. So this is going to be QS double prime multiplied by A. Let me differentiate here. So this area is often not the same area as the convection. So I'll call that AQ. Okay. right? So that term just kind of comes right on down. And then for the thermal production, this one also, there's not much we can do with this because there's, you know, there's typically no way to represent thermal production in terms of temperature. Thermal production is kind of a separate thing. And so this is just going to be Q dot multiplied by the volume. Okay. All right. And then for the radiation heat transfer, I'm just going to go ahead and neglect that for now. I wanted to show you that it can typically be part of the energy balance, but for most practical situations, we're not going to solve for it. And in fact, if we did want to solve for it here, it would actually make our solution nonlinear, which is a pain to deal with. And so, you know, for the radiation, we're just going to ignore for now. But we'll bring back radiation kind of near the end of the semester. Okay. And if you want a reason why we're ignoring this, is usually negligible. Okay. Again, unless you're doing kind of space application. And mathematically, it's really hard to deal with because radiation is actually proportional to the temperature raised to the 4th power, which is a pain in the butt to kind of solve for. Okay. So here's our equation. And so, of course, let's go ahead and simplify this. A question from the chat. So even though I changed, so for the area that's multiplied by the heat flux, I changed it from AS to AQ. The reason I changed this, no more cosmic. The reason I changed this is because oftentimes the heat flux is not applied on the entire surface area. It's usually only applied on just a small section of the object. Yeah. So yeah, it's a good observation. Yeah, so AQ, AS are different. Convection usually takes place around the entire object, but then the heat flux usually is only on a small portion. You'll see what I mean by that when we do an example right after this. Yeah. Okay, so let's go ahead and simplify this. So to simplify, all I'm going to do is I'm going to divide everything by rho VC. Everything with temperature, I'm going to move to the other side of the equation, and everything else I'm going to keep kind of as it is. Okay. So after we simplify, we end up with the following equation. We have dt. Okay. Usually when you have a differential equation, kind of the tradition or the standard form is to make your highest order derivative have a coefficient of 1. And so that's kind of what we do here. Okay. Plus HAS all over rho V times C times T. Okay. So that's familiar. So that comes from our convection term. Okay. This is equal to HAS divided by rho VC T infinity. Okay. Plus QS double prime times AQ divided by rho times V times C. Okay. Plus Q dot. So in this case, the volumes are going to cancel out. And so we divide by the density and the heat capacity C. Okay, and so what we have here, this is the general lump capacitance equation. Okay. So when a problem asks you to start from the general lump capacitance equation, this is kind of where you would start. So you kind of start with this equation. You can plug in the numbers if you want. And so, you know, if the problem gives you numbers, you can plug it in to kind of make that simpler. But this is kind of your starting point. Now, you're not going to use every single one of these terms in every situation. So usually the first step after you write down the equation is you're going to cancel out some of these terms which may not be relevant for a given problem. So, for instance, thermal generation. So thermal production, the Q dot term, may not be relevant or may not be active for every problem. And so, it's kind of the same as our heat equation problems, where you have to kind of read the problem, see what's relevant, see what's active, and cross out the terms that are not relevant. Okay. Okay. All right. So you'll see an example of that in the next one. Okay. All right. But before we jump into an example, are there any questions on this? Okay. Oh, by the way, one thing that you can do, and so some of you may have noticed, is that I've left this entire equation in terms of temperature T. If you want to solve this in terms of excess temperature theta, you can do that. Okay. And so if you do that, then theta here would replace the temperature there. And most importantly, it would take both these convection terms and kind of lump them together into one. Okay. Remember, theta here is equal to T minus T infinity. So it would simplify your math a little bit. Here, it wouldn't actually do all that much, because you're probably going to have a non-homogeneous equation anyway, because you have heat flux and maybe thermal generation, but you can definitely do that as well. But because in most cases it doesn't really help you mathematically, I'm going to kind of move forward and kind of solve this in terms of just regular temperature, but you can of course solve in terms of excess temperature as well if you wanted to. Question? Yes.
Will this general Bassett's equation be used in the reference in one second?
It is, yes. Yeah. So this one you do need this for the homework. Yes, yeah. It should have been the last problem. I think it's like preheating an oven or something like that.
Yeah,
So
well, it was like-
exactly. Yeah. Okay, so let's do an example. So you can kind of see this in action. Okay. Okay, so let's consider a situation of, let's say that you are preheating a cast iron skillet for you to cook your dinner. Okay. So for those of you who have cooked on one of these things, you know that it takes forever to kind of heat up sometimes, just because it's so heavy and so dense. But once you've heated up, it's great for cooking things. And if you take good care of it, this skillet will probably last you for your entire life. Okay. Okay, so let me go ahead and draw it. This is not sponsored, by the way, but the cast iron skillet that I have is a Lodge brand, and I love it. So if Lodge, if you're watching this, or you want to give me some money, I would definitely be open for that. Okay. There you go. Not sponsored. I'm just a fan of the product. Okay. Okay. So let's say that we're preheating this skillet here. So usually you're going to preheat it over a stove. Okay. So you have a flame that is kind of kind of heating it up from the bottom. Right. All right. So the way that we're going to kind of model this heating here is we're going to say that this flame is applying a prescribed heat flux on the bottom of the skillet. And so let's say that it has a value. Well, this one I don't have numbers. And so let's say this one gives a heat flux of QS double prime. Okay. Okay. And so at the same time that you're heating it, you also have airflow that's going over the top. Because typically, if you're going to cook something in a cast iron skillet, usually, it's going to smoke to a certain degree, and so you need to turn on your hood fan in order to make sure your entire apartment or your entire kitchen doesn't get filled with smoke. Okay, and so we're going to have a convection that's going over the top. Okay. And so that convection is going to have a convection coefficient H and an ambient temperature T infinity. Okay. All right. So let's assume that we're preheating this just from neutral. So we're going to assume that the skillet starts at room temperature. Okay. And so let's compute two things. Okay. So first thing we're going to compute is we're going to solve our general lump capacitance equation. All right. And what we're going to obtain from that is the time evolution of temperature in the skillet. Question, yes.
Are you ignoring the BR number for this?
Yeah, that's a good question. We're gonna compute that later.
Oh,
Yeah.
you are.
Mhm.
Okay.
Okay. All right, number two. Number two is, usually if you're cooking with something in a cast iron skillet, you usually want to heat it up to a point where, typically what they say is you heat it up until whatever oil that you're using, cooking oil, starts to smoke. Okay. And so we want to compute how long it's going to take in order to reach that point. That's T smoke. Okay. Actually, Blake, I apologize. We're not going to solve for the BO number here because we don't have any numbers. But typically, you would, just to verify that the non-capacitance is valid, you would have to compute the BO number in this situation. So we're going to assume. Let me add that to our assumptions here. So we're going to assume that the BO number for this situation is less than 0.1. I'm thinking of another example. Yeah. Okay, so this is a pretty standard lump capacitance equation. So we're going to need to use our general equation because we do have a prescribed heat flux. But besides that, we're just going to continue, as it is. Okay. Any questions on this example here? Okay. All right. So let's go ahead and compute these or carry out this example here. Okay. All right, let's start with part one of the problem. So part one, we want to solve for the time evolution of temperature. So let's start with the general lump capacitance equation. And first thing, let's cancel some terms that are not going to be valid in this case. Okay. So let's write our general lump capacitance equation again. So our general lump capacitance is dt, dt plus HAS over rho V times C times T. Okay. Is equal to HAS over rho times V times C T infinity plus QS double prime AQ divided by rho times V times C plus Q dot over rho C. Okay, so when the problem kind of asks you to start with the full lump capacitance equation, then you can start with this one. Even for the ones that are just convection only, you can start with this one, and you can just cancel out the heat flux and cancel out the thermal production, and you'll end up with the same lump capacitance equation that we had previously. Okay. Okay. So with this one, we don't have that many cancellations to make, and so the only cancellation we have is the thermal production. All right, and then we're left with the following, equation there. Okay. Question, yes.
So I know, like in the future, like if I were to like do this problem on my own, I would think that the flame was, an example of thermal production. Why is it not an example?
Yeah, that's a good question. So yeah, technically speaking, the flame, you can consider it as the production of thermal energy because you're burning probably gas or you're burning some kind of fuel and you're producing heat. But this equation that we're solving for, you have to think about kind of what we're considering. And so in this case, we're considering only the skillet by itself. And so our control volume in this case is only going to go around the skillet itself. Yeah, because we're solving for the temperature of the object. And so if we included the flame, then we may have to adjust how we consider the temperature itself. But since we're just doing the skillet, because that's going to be the thing that we're solving for, then we include the flame as a heat flux, not as a thermal production. Yeah. Okay. So that's the only cancellation that we're going to make here. Cast iron usually is an inert material, so it's not going to produce any heat. So let's go ahead and solve this. And so if you want to make your writing a little bit easier, you can substitute excess temperature. It's a little bit less writing to do. Yep.
Is there any example where a thermal production might induce heat flux?
Ooh, that's a good question. And so in those situations, maybe the object is kind of producing temperature enough on its own. And maybe if it's so big that it starts to radiate heat to the environment, then that would be a case where, you have just so much thermal production that it's getting heat flux out into the environment. And so in that situation, you would have a positive heat flux, positive thermal production, but then your heat flux would be negative because then your object would be losing heat due to the heat flux. Yeah. Okay, so you can substitute excess temperature. Remember, its excess temperature is theta is equal to T minus T infinity. Okay. So that's going to simplify our math a little bit here. And so what that's going to do is it's going to allow us to combine both of the convection terms. Okay. Okay, so if we combine both the convection terms, we have d theta dt is equal to, d theta dt plus HAS over rho VC times theta is equal to QS double prime AQ over rho VC. Okay, so a little bit easier to solve in this case. Okay. Oh, by the way, I guess going back to Kiera's question from earlier too, This AQ right here, remember this AQ is only the area that is being acted upon by the heat flux, okay? That's why we have them separate. So for the convection, we have A sub S. For the heat flux, we have A sub Q, because oftentimes this is going to be different. Okay. And for this problem, you know, it's hopefully it's pretty clear why these are different. Because the flame is not heating up the pan all around it. The flame is only heating up the bottom of the pan. And so in this case, our AQ is only going to be the surface area of the bottom of the pan itself. So kind of remember, kind of keep that in mind. So that area there is often different. Okay, so let's go ahead and solve this this ODE. And so we have a first order linear ODE with constant coefficients, but it is non-homogeneous. And so we do have a non-zero right-hand side. And so the typical way that we solve this is through a technique called integrating factor. So hopefully that rings a bell from, you know, either Math 250B or EGME 308, okay? And so just to kind of refresh your memory, the way to solve an equation with integrating factor is we look at the term. We look at the term that has our solution variable just by itself, and we take the coefficient in front of that, okay? And so in this case, we're ultimately solving this equation for theta. And so we want to look for the term in our differential equation that has just theta by itself, okay? Which is the term that I've boxed here, okay? What we're then going to do is we're going to take the coefficient in front of theta, and that's going to form the basis of our integrating factor. And so in this case, our integrating factor, usually I use the symbol mu, okay? Mu of t is going to be equal to E raised to the HAS over rho VC, okay? So that's the coefficient in front of the theta term in our ODE, okay? So we're going to take that and put it in the exponent there, and then we're going to multiply it by t, okay? All right. And so what we do with the integrating factor is that we then multiply the entire differential equation by this integrating factor. And so what we have from there is we have mu of t multiplied by d theta dt plus HAS over rho VC times theta is equal to QS double prime AQ divided by rho VC times mu of t. Okay. So it's just our original equation multiplied by our integrating factor. Okay. So I've done it to the left and right side of the equation. Okay. So the magic of the integrating factor kind of happens on the left-hand side. And so by multiplying by the integrating factor and just by having our integrating factor take this form, this left-hand side, we can then change it to a, you know, I call a pre-product rule. So it's like a reverse product rule. And so what that means is that it turns the left-hand side into what I call a perfect differential. So we have d dt of theta times mu of t. Okay. And so the reason I call this pre-product rule is that if you kind of evaluate this via product rule, and so if we kind of take the derivative of the first, which is d theta dt times mu of t, and then we take the derivative plus the derivative of the second multiplied by the first, and so that's d mu dt theta. Okay. This expression is actually the exact same as what we have up here. Okay. So we just kind of do product rule in reverse. And so we have something that looks like a product rule, and we replace it with that product rule itself. Okay. And so in case you kind of forgot kind of why we do the integrating factor to begin with. Okay. Right-hand side stay the same. So right-hand side is still going to be QS double prime AQ divided by rho V times C mu of T. Okay. Okay. And so the benefit of having this form right here is that we can just simply just take the integral of both sides. Okay. And so we take the integral of both sides here. We take the integral with respect to t. Okay. So the left-hand side, we have a perfect differential. We have a perfect kind of derivative here. That's going to cancel out with the integral. And so left-hand side, we have theta of t multiplied by mu of t. Okay. Is equal to integral. And so at this point, in order to perform the integral, we do have to plug in for mu. And so we have q s double prime aq divided by rho vc. All of those terms there are constants. The heat flux, the surface area of the bottom of the skillet, the density, the volume, the heat capacity, all those are constants. So, you know, they come out of the integral. Okay. And then we have integral of, I'm going to go ahead and plug in for mu. So that mu here is e raised to the HAS over rho VC times T dt. Okay. Okay. You can go, at this point, we can plug in the integrating factor on the left-hand side too. So we can go ahead and do that. And then on the right-hand side, let's go ahead and evaluate that integral. So that integral, I'm just going to take the exponent and divide by it. Okay. So on the left-hand side, we have theta of t multiplied by e raised to the HAS over rho v times c times t is equal to QS double prime times AQ divided by rho VC. We perform this integral. And so the integration factor that comes out is rho VC divided by HAS. Okay. And that's raised to multiplied by E raised to the HAS over rho VC times T. Okay. And since we did an indefinite integral here, so we did an integral without any bounds, we have to add an arbitrary constant c. Okay. And so from here, it's just kind of algebra and arithmetic to kind of simplify this. And so first thing we see is that we have a rho VC and a rho VC going to cancel out on the right-hand side. Okay. Let's solve this expression for theta of t. So theta of t, let's multiply it by, well, we're going to divide by the integrating factor. Okay. So after simplifying and solving for theta, what we get is theta of t is equal to q s double prime aq over HAS. Okay. Plus C E raised to the minus HAS for rho BC T. Okay. So crash course in differential equations again, hopefully, and I know I went a little bit fast with that, but, hopefully you guys have seen integrating factor before. Okay. All right, any questions on how I got this result here? Question, yes. Oh, yeah, for sure. Mhm. Mhm. Okay. So that right here is our solution, but remember, it's just a general solution, so it's not the full solution just yet. Okay. So in order to solve for the full solution, we need to obtain a value for this arbitrary constant. Okay. And the way that we're going to do that is we're going to apply our initial condition. Okay. So basically, we need to plug in the situation. We need to plug in the the temperature of the pan when time is equal to 0. Okay. So when t is equal to 0, okay. If you kind of scroll back up to kind of the beginning of the problem, one of the things we stated was that the pan is going to start at room temperature. I keep calling it a pan, but it's a skillet. Right, so that makes sense. And so, you probably just pulled the skillet out from your cupboard. And so it's probably just the same temperature of whatever the room that you're in, okay? Which is also the same temperature as the air that's flowing on top of it, right? And so we say that T, when T is equal to 0, is equal to T infinity, okay? If we put this in terms of excess temperature, what this tells us is that excess temperature when T is equal to 0, right? And so when time is equal to 0, there is no excess temperature. And so, that means theta when T is equal to 0 is going to be equal to 0. Okay. Okay. So let's go ahead and use that and solve for C. Okay. So we have theta of 0 is equal to 0. And let's plug in our general solution here. So we have QS double prime AQ divided by HAS plus C E raised to the 0. Okay. E raised to the 0 here is just 1. And so this very quickly tells us that C, our arbitrary constant, is minus QS double prime AQ over HAS. Okay. All right, and so if we plug that in, we get theta of T is equal to QS double prime AQ divided by HAS minus QS double prime AQ over HAS multiplied by E raised to the minus HAS over rho VC times T. Okay. And that right there is our full solution there. Okay, I know we're out of time. There is a couple of things I want to comment on this, but we'll pick that up kind of first thing on Thursday. But just because I know this is a problem that's asked in the homework. The problem, a lot of these problems might ask you if your problem is going to reach a steady state temperature, right? So just very quickly what that means for those of you who are working on the homework, right? So first thing, a problem might ask you is that does this problem reach steady state? And so steady state is the temperature when T approaches infinity. Okay. And so if you look at the solution here, there is one term here that's going to go away when T approaches infinity, which is this term right here, because we have that decaying exponential, okay? And so in this case, we do have a steady state temperature. And so our steady state temperature is actually going to be this term right here, which does not have any exponential. Okay, but I wanted to mention that really quickly just because I know it's on the homework. But we'll kind of touch on this again at the beginning of class on Thursday. So I apologize for going late today. Thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you on Thursday.
Old exam.
I do, yeah. So I can post well, that's 2022. So I'll post that example.
No, let me see it.
Yeah.
Oh,
What's up?
I came in late today.
I have a question. Yeah, so the due date is March 2nd. Yeah, but I know on Canvas it says February 28th, but due March 2nd. Gotcha. Yeah, because I'm not going to grade over the weekend. Gotcha. Yep. Yeah. Looks like it was a part of the problem too. Oh, it's because of this. It's because you kind of show off.
Oh. I guess, yeah, a lot of.
That's, it's okay in the lecture when there's a minute time. But
Said you could go over a bunch of examples today, so.
Yeah.
Also, like, when you choose the.
Yeah.
I could understand because of like.
Yep.
I think you can miss a lot too.
Yeah, so integrating factor, that's a technique that we use called first order.
Maybe you
equation.
should read honestly.
So what we have is a first order differential. So we have
I
call this a
so
non-homogeneous
that's all that's okay.
And so integrating factor gives us a way to solve this. You can't solve this.
Yeah. Which.
And so the way to do that is it's kind of a
That
trick where
one's
we say,
the worst one.
find this integrating factor here, and we multiply
I,
this by
I
the
like
equation.
linear versus.
Then what we can do is we can do the kind of pre-product where we turn that left hand side, which is the derivative of beta multiplied by the n one.
1, 2, and then he's giving us another one.
Exactly,
One,
because
two,
if you actually,
and
so I
then
know I did this kind of.
quizzes.
But it's actually, if you take. Use this guy right here, you get HAS over rho B C to that term that comes out to the derivative, times e to the this times t.
I'll go, yeah.
This is exactly what we have right here. And so we kind of multiply by this, kind of do the reverse product rule. So that we get this term, which is the perfect differential. And then we can take the integral of that to cancel that out. So it's kind of a trick to kind of simplify the left hand side into something that we can just integrate really easily. Yeah.
And then it's always like this, right? 'Cause
It is,
I remember
yes.
that, but, like, does this just like come along with it? Like.
Yeah, so actually, so I skipped a step here. So typically the integrating factors, we have an integral of this times this, but since this is just a constant, I just kind of skipped that step and said just percentage.
Okay, for sure. Thank you.
Yep. Yeah, you win? Congrats, man. Sick. When was the competition? Oh, dang. Dang, yeah. Wow. Oh, I'm sure. Yeah. Do you eat anything? Coverage?
Whenever I see it.
Nice. Congrats, dude.
Yeah.
You were making a couple of events too. So we got gold in that draw. Dang, that's crazy.
It's a lot more.
Congrats.
Thank you, bro. It was tough though. It was tough.
Being able to-
I'm so covered so bad. Like it's already been 3-4 days and I'm still like, you know.
Okay.
Yeah, here's a little video one of my guys made for me.
today.
Nice.
Dude, I had a exam for my.
How much are you
last
thinking?
Bench, so this right here is a tenth, this is.
The teacher.
Dang,
30
dude.
questions on it.
That's more than,
And
that's two of me.
I need to do like all of the work. And like
Crazy.
give them a multiple choice, but like you still have to do
Here, this is
the
a
right
five.
answer.
Dang,
And it
oh
was
my
like,
God.
I didn't even have enough time to finish it.
You know, I had a Super Bowl party in my place, and then there, have you seen the video of Jalen Hurts squatting
Yeah.
like 600 pounds?
Yeah.
I showed that to my friends, they're like, that's great.
It's insane.
That's nice. That's awesome.
Thank you.
Oh.
Eat some, yeah. I hope he recovers soon.
Yeah.
I'm still trying. Alright, what do you want to?
See ya.